Thanks, Michal. So, as you said, I'm Shahaf. I'm a PhD student at the Hebrew University. And in this talk, I'll be talking about, I will be talking also about guarantees, but specifically about the computational complexity of explaining ML models. And I'll specifically be talking about a few different works as we go along. So let's start with motivation and talk about why do we even care about the computational complexity of finding explanations. And I'll try to address this in two ways, in two different aspects. The first is the more practical side, which is just basically understanding which types of explanations and with different types of guarantees we can compute efficiently and which are hard to compute. And I'll also talk about what I mean by guarantees here. And the conceptual or more theoretical aspect you can see of this is an alternative way or form of mathematical, another perspective to view interpretability. And I'll try to explain what I mean by this as well. But let's start with the first part. And before we dive into this, let's start with the basic question and ask, why do we even care about provable guarantees in explanations? So I'll give a few different examples. Here is the first one where we have a classifier, a neural network classifier that gets some image. This is an X-ray image, and it classifies this to be pneumonia, which is a lung disease. And the user, in this case, maybe a physician, wants to understand the logic for this prediction because the neural network is, of course, a black box. So a classic way to address this is to throw this at some XAI method. So here is an example. I'm sure you all know about Lime and Chap, where you get some attribution for each one of the features. And then in many cases, what is done is you can perform some feature selection where you just choose the K features with the highest contribution, and you can show this to the user so they would see which are the important features for predicting this test. In many cases, as you all know, explanations like this can be very fragile or sensitive. So in this particular example, we can take this explanation and pass it through our model and get that the classification is pneumonia, which is good because this is actually the important features. So this is an expected behavior that we will get the same classification. But when we add one feature to the explanation, we actually get an opposite behavior where the input is, the explanation is classified as not pneumonia. And this is just a simple example to show you the sensitivity and fragility of explanations to small perturbations. And one type of guarantee that we can use to overcome this is what's called sufficiency guarantees. And sufficiency guarantees are defined in the following way. So if we have a model F and an input, for example, this input as a beagle, so we can try to find subsets where we know that whatever we put in the complementary of this subset, the classification will remain the same. So this subset is sufficient to determine the prediction. This is actually an example from images that are taken from the Ancor's paper for whoever knows this paper. So here you can actually see this definition, this in practice where we plug in different complementary values to the feature and the classification always remains the same. And we say that this is this subset satisfies sufficiency, and particularly we'll call this a sufficient reason. This is like a common term that is used in the literature. And this is a bit of an extreme notion of sufficiency, that for anything that we put in the complementary, the classification will remain the same. And there are many relaxations of this definition as well. But for now, I'll stick to this basic notion. It is also commonly assumed that smaller subsets that we are selected provide a better explanation because they contain less features. So an additional guarantee that people have been looking at is minimality guarantees. So we want this subset to satisfy both sufficiency guarantees, that fixing it will determine the prediction, and also minimality, that it would be as small as possible. By the way, if you have questions during the way, you can ask, so feel free. For the second example, for guarantees that could be of interest, or why guarantees are important in general, we have this classic example of loan prediction task, where applicant wants to get a loan from a bank, and there's a bunch of details that the bank takes and runs it through a model. And in this particular case, this loan is rejected and denied, and the user would want to explain this phenomena, this prediction as well. And in this particular case, one popular thing is what's called a counterfactual explanation. And the counterfactual explanation is some change to the input that you can change some of the features, such that if you the change in these features causes the prediction to change as well. So in this particular case, we are changing the amount of the loan that is requested, and also the duration, and this will cause the loan to be accepted. And people like this explanation in this particular context because it's an actionable explanation. Or in other words, it provides a user for what needs to be done in order for the loan to change from rejected to accepted. Here as well, guarantees can also be very important. For instance, one important guarantee here is also the guarantee of minimality. Because if, for example, there exists a different counterfactual, which is much closer to the original, meaning that the explanation is not minimal, this could be, of course, a bad thing, meaning that counterfactual explanation that we gave to the user is a bad one, because we could provide a much smaller change. And of course, people have been looking at other types of provable guarantees in the context of counterfactuals, but minimality is, of course, central. Okay, here's a third motivating example, which will be the last one. We have a tabular data task for detecting breast cancer malignant patients. And this is, again, a physician that uses this model, for example, and wants to understand the task, wants to understand the prediction. And the classic explanation method that we all know is SHAP. And SHAP is just a game theoretic way to allocate the contributions of each one of the features. So SHAP will generally give us something like this, which quantifies for each one of the features how much it contributed to the prediction. And one of the reasons that people like SHAP very much is because SHAP, the Shapley values that are the basis for SHAP, satisfy 4 guarantees that are considered very important in interpretability. One of these, for example, is the dummy axiom. These are called axioms in game theory. One of them, for example, is the dummy axiom that says that if, for example, a feature doesn't change the model output at all, it should get a 0 contribution, which is something that we indeed would assume should hold for any feature attribution method. In this particular case, the meaning would be that the tumor size didn't contribute, because we can see that it had a 0 prediction, a 0 contribution in the Shapley values. The problem that here too, usually what is done when people compute SHAP is an approximation. They use stuff like kernel SHAP, which is a heuristic that approximates SHAP, and it doesn't actually compute the true Shapley values, the exact Shapley values. And this is because Shapley is, in many cases, computationally hard to compute. And in general, this will just mean that the axioms are not necessarily satisfied. So the reason that we like Shapley values so much is because of these guarantees. But if we are just looking at a heuristic that approximates them and it's not the true Shapley value, then the guarantees are not guaranteed to hold. And again, this could be something confusing or a problem if we are using these explanations in safety critical systems. Okay, so I'll continue. Yeah, so generally, as I said before, many of these explanations are indeed very computationally hard to compute. So I talked a bit about some of them, the exact Shapley values, the sufficiency and minimality, the counterfactuals, and we have lots of other guarantees in explanations. And in many cases, computing these guarantees, explanations with such guarantees, is computationally hard. And for this particular reason, there is a theoretical interest, big theoretical interest in understanding the computational complexity of finding these explanations. So we can better understand what types of explanations and what types of guarantees we can or we cannot find based on these complexity results. Okay, so I talked about this practical side. I hope I persuaded you that it is interesting. I'll also briefly touch on this other part, which is an alternative or formal view of interpretability based on computational complexity. And generally, interpretability, as you know, is defined, this is from Wikipedia, it's defined as the extent to which humans can understand the causes of decisions made by ML models. But unfortunately, we are still lacking a mathematical understanding because this definition talks about humans. We're still lacking mathematical understanding of what it exactly means for a model to be interpretable. And lots of things are thrown around in the literature, lots of claims, for example, very known claim that decision trees are more interpretable than neural networks, or that linear models are more interpretable than neural networks. These are all claims that we all assume to be folklore generally. But we would theoretically want to have some mathematical tool to talk about what it exactly means mathematically that the decision tree is more interpretable than neural networks. And there are actually lots of different formalizations, interesting formalizations that were suggested in the literature. I'm just going to talk about one of them. Of course, it's not the correct way, but just another potential mathematical way to look at interpretability. And this was actually suggested already in 2020 based on computational complexity. And the idea is that we can look at the complexity of generating different types of explanations. And if we see that we can compute explanations with different guarantees for a model efficiently, meaning that we can explain its decisions easily, computationally, then we can regard it, at least from this computational perspective, as interpretable, because we can explain its decisions easily, computationally. If generating explanations for the models is consistently intractable, we would assume that the model is computationally uninterpretable because it is computationally hard to generate these types of explanations. Of course, this is only an additional view of interpretability, and there are lots of different definitions in the literature, but just another formal or mathematical perspective of looking at it. Okay, so I talked about the general motivation for why it's interesting looking at complexity. And let's start to talk about specific concrete results. So what are the factors that impact the computational complexity of finding explanations? And I'll start by talking about the first most, I guess, fundamental types of factors, which is the model type and the explanation type. And I'll specifically refer to results from this paper, which is actually one of the first papers that talked about this topic of computational complexity of explanations from Barcello et al. In Europe's 2020. Okay, so what they did in this paper is they looked at three classes of models, types of models, which is linear models, decision trees, and neural networks. So we have the entire spectrum of interpretability, and they looked at different explanation types and analyzed or proved the computational complexity of finding each one of these explanations. So for example, if we look at the definition of a minimum counterfactual explanation, you can see that for linear models and decision trees, These can be computed in polynomial time, even in linear time in many cases. So this is efficiently computable. But for neural networks, this task becomes NP complete. And this is in some, you can think of this as some, again, formal way of looking at this aspect that neural networks are less interpretable than linear models and decision trees, which is what is commonly assumed in the literature. And you can see how the complexity results here align with this folklore understanding. You can see that the complexity for explaining the decisions of the neural networks are indeed harder than for the interpretable models. When we look at the minimal sufficient explanation, then you have this hierarchy of results, where for the linear models, it can be solved in polynomial time. For decision trees, it's NP complete. And for neural networks, we have this ugly thing, which is called sigma P2 complete. And for those of you who don't know, this is the second order of the polynomial hierarchy, meaning that it's a complexity class that is above NP, meaning that this is sort of like NP squared. So this is a complexity class that is even or much harder than NP. So here we have this hierarchy of the decision trees being harder to explain and the neural networks being the worst in this particular case. We have this additional notation, which I won't get too much into the precise definition of counting completions, but generally it talks about giving a subset that you fix, calculating the probability that under perturbations, the classification will remain the same. So it's a probabilistic notion of an explanation. But what's important to see here is this behavior. So we have here the P-sharp complexity class, which is again tasks that are very, very hard. This is a counting complexity class, so this is a very hard task, much harder than polynomial. And what's important to see here is two different things that I wanted to point it out. The first is that there is no strict verdict between decision trees and linear models in the complexity. So it's true that both of these models will always have a lower complexity than neural networks because they are both strictly less expressive than neural networks. We can reduce both of these models to a neural network. So for this particular reason, you'll always have the complexity class in the neural network higher. But between these two types of interpretable models, you can have these distinctions in complexity. Sometimes the complexity will be harder for decision trees, and sometimes it will be harder for linear models. It depends on the explanation type. The second fact that I wanted to point out is the very fact that the explanation computations are intractable even for the interpretable models. In other words, finding some types of explanations with some types of guarantees can be computationally hard to find even for the interpretable models, even for the models that humans usually consider as interpretable. And this, of course, raises questions about the interpretability of these models, because we see that some important guarantees are actually computationally hard to find, even for these simple models. Okay, so we talked about the first two factors, and now we'll move to the third factor, which is the explanation scope, or in other words, local and global explanations. So just a short recall, the difference between a local explanation and a global explanation is that a local explanation is an explanation for a specific input, meaning that we're explaining a specific prediction. And the global explanation is an explanation that is provided over an entire domain of interest. So its purpose is understanding something about the decisions of the models globally. And in this paper that we presented in ICML 2024, we talked about some of the distinctions in complexity between local and global explanations. Okay, so let's see one example of these instances. So we have this local prediction of a model. We have this model F that classified this blue image to class 1. And this is, we want a local explanation, meaning to understand this particular prediction. And one type of explanation that I already discussed before is this notion of the sufficient explanation, sufficient reason, which is this subset that if we fix these features to their values, then the prediction will remain the same regardless of what we put in the complementary features. So these three features here are free to take in on any possible value, and the classification will always remain class 1. As you can see here in the example, this is another visualization to emphasize this. So a global sufficient reason in this particular case would be the exact same definition, only now instead of defining the sufficiency over one specific input, we will define the sufficiency for any input in the domain of interest. So the sufficiency will hold for a bunch of inputs. And so it holds globally in this sense. Okay, so what happens to the complexity when we move from the local to the global variance? So for linear models, we have a relatively expected case where you can see that the global variant is harder to compute than the local variant. So we have this gap in complexity. So finding these sufficient reasons, the global variant is harder than the local variant. And interestingly, in decision trees and neural networks, actually the opposite occurs. So actually, in these models, what happens is that the local variant is actually harder than the global variant, which can seem a bit unexpected. And let's try to understand why mathematically this happens. This happens based on the following property, which shows that in the local case, we can have an exponentially number. We can prove that there is, in the worst case, an exponentially number of minimal sufficient reasons, locally minimal sufficient reasons. So this could be a local minima, this could be a local minima, etc. So we can have many such subsets. However, for the global variant, we can prove that there exists one unique subset that satisfies this sufficiency, this global sufficiency, which is a stricter guarantee. And this property particularly is what makes the global task actually in many cases easier than the local task, because in the local task, when we are looking for a minimal subset, we have a bunch from an optimization perspective, right? We have a bunch of different subsets to choose from, an exponential abundance. But in the global task, we only have one minimal subset that we will always converge to. So this is actually what drives this weird behavior. But for linear models, I won't get into too much technical details of this, but for linear models, we have some model-specific behavior, which is relevant to the fact that in a linear model, we can calculate the exact local contribution of each one of these features by looking at the weight times the prediction in that input, which will give us the exact local contribution. And by looking at these contributions, we can perform some sorting of the features and develop an algorithm which is specific for linear models that lets us solve this task efficiently in the local case. And this is not possible in the global case. So in linear models, we have this weird model-specific behavior that shows us that the global variant is harder than the local, and in the other models, this isn't the case. So we have this very sensitive behavior based on the different explanation types, the explanation forms. Yeah, so in the paper, we generally look at other forms, other comparisons of local versus global explanations other than this one. So if you want, you can check that out in the paper. And I think I showed some examples for how this scope can impact the complexity. And I want to move on to the next aspect, which is the aspects that are related to the structural parameters of the model that can affect the complexity. And this would be similar to or related to the first point that I talked about, the model type and how that influences complexity, but I'll try to talk about this here in a more fine-grained way, meaning how different attributes or parameters that are related to how the model is built can influence the complexity. And I'll specifically talk a bit about results from this paper, which is a paper we presented at ICML 2025, which specifically talks about the complexity of finding explanations for ensemble models. So this is our focus here. So a short recap, I'm sure lots of you know this, but an ensemble model is just a model that aggregates a bunch of independent models, independent base models, and aggregates the results. So the aggregation can be done with many different schemes. One popular scheme is majority voting, but there are other ways to do this aggregation. It could be averaging, weighted voting, or other ways. And the purpose is ensembles can serve many purposes, such as reducing the noise and also improving the accuracy in many cases. So these are a really popular family of ML models. A classic example is random forest, which takes a bunch of decision trees, performs a majority voting over the decision trees, and gives us the final class. From an interpretability perspective, it is very widely acknowledged that ensembles are not interpretable models, or in other words, they are black box models. And here we have again the distinction between the individual models in many cases, like the decision trees in a random forest, where each one is considered interpretable, but the ensemble as a whole is considered a black box. And this happens due to the reason that when we are aggregating all of these results together, it is much more complicated to understand the logic behind the decision. So for this reason, I think, and if you are following until now, I think it wouldn't surprise you that the complexity for finding explanations for ensemble models, as we were able to prove in this paper, is in many cases harder for ensembles than it is for the individual models. Which again aligns with the human perception of interpretability. But what we also wanted to look on in this paper is to better understand how the structure of the ensemble, or the structural parameters of how the ensemble is built, impacts the complexity. And we do this specifically with a branch of computational complexity, which is a very popular and well-known branch called parameterized complexity, which looks at different structural parameters and how each one of these structural parameters affects the complexity. So we're bringing these concepts here to this context. And the two parameters that we were looking on is the size of each base model in the ensemble and the number of base models in the ensemble. So how do these two fundamental factors of the ensemble impact the complexity? So for the first parameter, which is the base model size, we were able to prove a very negative complexity result, which shows that for a wide variety of different types of models and different explanation types, finding explanations is already computationally intractable with only a really small number of models in the ensemble. So even when this is a constant, and specifically even 3 in many cases, depends on the exact explanation type, but even if we are looking at an ensemble that has many tiny models, still as a whole, generating explanations for it is still computationally demanding. It's still intractable. And in other words, this tells us, maybe as practitioners, that if we try to shrink the sizes of each one of the models in the ensemble, it will not help us in finding these explanations, these guarantees more efficiently, and the ensemble as a whole still remains intractable to explain. However, when we look at the number of models in the ensemble, there is a different behavior, which is a mixed behavior depending on the model that you have, the model type that you have in the ensemble. So if we are looking at decision trees, we show a positive result where a small number of decision trees in the ensemble, when we look at a fixed number of decision trees, then finding many types of explanations can be computed efficiently. However, if we are looking at different types of models, such as linear classifiers, we can show that already with two models in the ensemble, then already there is an exponential explosion and the complexity becomes intractable. Or in other words, this tells us that in an ensemble, if we try to reduce the number of trees, if we're just talking about a tree ensemble, then we can make the computation of explanations efficient. But if we're trying to do this for an ensemble that contains these linear models, then this would not help and the complexity will still be intractable. If we're looking only on tree ensembles and we're analyzing the results that we found in this paper, then what this gives us is this interesting comparison between these two types of choices of ensembles. One is an ensemble that has a small number of large decision trees and one that has many small decision trees. And from a computational complexity perspective, with relation to explainability, we can show that the first choice is much preferable, meaning that the explanation computation is much more efficient when we are looking at a small number of large decision trees rather than the other option. Okay, so I talked a bit about structural parameters in ensembles. We can do this similar analysis to this for other types of models. So I won't get too much into this because lack of time, but for example, in a neural network, we can also look at different aspects of the neural network that can affect the complexity. For example, the width of the neural network, the depth of the neural network, other maybe topological factors. And actually in a recent paper that we will present in NeurIPS, we were able to find some related results that shows complexity differences between width and depth in neural network for computing different types of explanations. So this will be a similar analysis, but for the topological factors of the neural network graphs. Okay, so we talked about how different aspects of how the model is built can impact the complexity. And I'll also try to touch on this aspect, which is the choice of the input domain over which we are providing the explanation for generating for the complexity of generating explanations. And specifically, talk a bit about results from this paper that we will present in NeurIPS, which is actually a joint work together with Michal. And in this work, we specifically looked on the complexity of finding explanations for additive models, for GAMs. So if you're not familiar with what is a GAM, a generalized additive model, so a GAM is a very popular interpretable model that is used, where we are combining, adding up each feature by independent model contribution, exactly as you see in the formalization here. This is how it's exactly defined. And this gives us, these models are considered much more interpretable because it allows us feature by feature evaluation of how each feature affects the model's output. And in the classical literature of GAMs that were suggested many years ago, each one of these features is was usually used as what's called a spline. And a spline is simply a piecewise polynomial. And this was also referred to as a smooth GAM because of their smooth structure. So this is really the classic definition of a GAM. But in modern literature, people are usually using each one of these components either as a neural network. And a neural network, when we're using a neural network as each one of these components, this is commonly called a NAM, or a neural additive model, or each one of the components being a tree ensemble. And in this particular case, the model as a whole is called an explainable boosting machine, or an EBM. So two of the most common ways to use GAMs today are either with the use of NAMs, meaning that each one of the components is a neural network, or with EBMs, that each one of the components is a tree ensemble. yeah, so as I said before, in this work, we looked at different aspects of the complexity of finding explanations for GAMs. And one of the things we found, and this is how it relates to the list of aspects that I talked about before, is that specifically in GAMs, there is a really high sensitivity for the complexity of finding explanations to the choice of the input domain. And if we are looking at this table from our paper that talks about the complexity of explanations in GAMs in many different settings, we analyzed the explanations in across three different types of input domain assumptions. The first is enumerable discrete, meaning that the input is discrete and each one of the points has an enumerable set of options to choose from. So this, yeah, can happen in a lot of practical scenarios. The second is the discrete setting where the inputs are discrete, but not necessarily enumerable. And the third is the continuous setting. And as you can see here, there is really a drastic variation of the complexity based on the choice of the input domain for the explanations. In the explanations that I highlighted here, all of these are explanations that are strictly easier to compute in the enumerable discrete setting compared to the other settings. And in this explanation type, it is easier actually in the continuous setting. So this is really an inconsistent behavior that changes based on the type of explanation that we're choosing. Another interesting thing to point out is that what we saw that happens in GAMs happens in stark contrast to other ML models, such as decision trees, neural networks, tree ensembles, so many other ML models that we can look at the exact same explanations. And there you can see that the complexity doesn't change at all when we are moving from these different types of input domain assumptions. But when we are specifically talking about GAMs, we show this really high variation in the complexity based on the choice of the input domain. And from a more practical perspective, this could be interesting because it tells practitioners on different options of input space transformations that they can do, which is actually something that is very popular in GAMs. For example, discretizing the input or other sorts of manipulations that can be done on the model in order to make the explanation computations tractable. All right, so I touched on this aspect as well that also affects the complexity. And I won't have time to get into this aspect too much because it requires a lot of details. But generally, when we're talking about the complexity of explanations, the distribution from which we are taking sampling inputs, at least in the probabilistic notions of explanations, also has critical implications for the complexity. We showed this that this happens in a few papers that we had. Particularly, this happens a lot in Shapley values because Shapley values are based on a calculation of an expectation. And when we're calculating an expectation, we need some probabilistic assumption regarding the distributions, such as feature independence and many other possible assumptions. And the different distributional assumptions have drastic influence on how hard it is to generate these explanations. So this is like another factor that along the way we saw is very impactful. And of course, there are lots of other things to look on in future work. I hope I gave you a brief outline of some of these important factors for the complexity. All right, so I'll move now to the conclusion. So I generally talked about computational complexity as a central topic for understanding, better understanding what types of guarantees for explanations we can find or we cannot find, what's possible and what's impossible, I guess. It also provides us with some fresh way to look, fresh and formal or mathematical way to look on interpretability by looking at the complexity for these different types of interpretable models. And we also talked about different factors that impact the complexity, such as the explanation type, the model type, the structural parameters, input domain, and much more. And this also brings forward a wide variety of practical either theoretical or also practical implications. For example, we can change, we can perform transformations for the input domain in order to make the explanation tractable. We can relax some of our assumptions regarding the model when we are training it. For example, the structural way we build the ensemble or a neural network in order for us to build a model where explanations can be computed efficiently. We can look at the distributional assumptions. So we can do lots of different manipulations based on these results in order to find explanations that are tractable. And for future work, things that we are looking on, and it would be great if more people would look on as well, is first looking on additional guarantees. So I talked about a few quite particular guarantees here: sufficiency guarantees, counterfactual explanations, Shapley values, which by themselves give us guarantees of interest. But of course, one can look at many other guarantees, and a particular emphasis in research and interpretability nowadays is on actionable guarantees, meaning guarantees that also give us something actionable that we can do with the explanation as well. So better understanding these types of guarantees is very interesting. Of course, some of the definitions that I talked about here can be very strict, and they can be in many cases relaxed. So we can look at different probabilistic or statistical relaxations of some of these definitions, which can in some cases maybe make an intractable explanation task tractable. I think that another very interesting connection that could be made is trying to connect some of these results with more learning theoretical perspectives, such as PAC. And this is something that wasn't done too much until today, but it's for sure a very promising direction to look at. And of course, we're also looking on results for other types of schemes that are discussed in current interpretability research, such as MECINTERP. So there is specifically a paper, not by our group, but by a different group, that discussed the computational complexity of finding circuits. Circuits are subgraphs of neural networks, which is a very common task in MECINTERP that people are looking at. So this is sort of an extension of some of the results that I talked about here to the MECINTERP area of research, which is a very interesting way to look at for future work as well. And this also opens up other avenues as well. That's it. Thanks for the attention. Would be glad to take questions.